It got suddenly quiet. So anybody thought about what they'd like to hear about on Friday? Any requests for odd topics? The only constraint is it can have nothing to do with the class. I have done small animal surgery. You want to hear about that? It's fun anecdotes, horrifying anecdotes. I'm not sure I want to tell those stories.
What was the question? What do you want to talk about on Friday?
What do you want to talk about on Friday?
Cornell in the 70s and 80s.
Cornell in the 70s. The history of slope day. Cornell in the 70s and 80s. I can talk about that a little bit.
No one cared. I don't know. I know one guy who went to Cornell during, it was like late 60s, early 70s, and like the school was in an uproar, and like
so in
professors weren't working or something.
1969,
Yeah.
in the spring of 1969, there was a near riot here.
Yeah.
And it resulted in an armed confrontation at Willard Strait with and various side effects, like every dorm room was summarily searched one weekend with no warning. I was living in a graduate school dorm at the time. You think you want to see a strange place, a grad school dorm. What kind of graduate students live in a dorm? You got it. They're either from very far away or they got no life. Well, there was no need to, because the Budweiser truck just pulled up at the bottom of the slope. So let's we'll save the stories for Friday. Like I say, the default topic for Friday is why the brain is or is not a computer. But for today, I'd like to talk a little bit more about motors. This is one of the fans that you're going to be using. This is an 80 millimeter CPU cooling fan, generic 12 volt, 0.15 amp motor. And you'll notice I colored half of the hub white on this motor with a whiteout. It's back in the day when you had to actually like type stuff, if you made a mistake, you could either retype the whole sheet, or you could take this white liquid and rub it on the sheet and then type over it. Have any of you ever actually done that? You have? Why? Why? Pen. Yeah. So use whiteout. Just cross it out. And of course, occasionally you still have to fill out a form on paper. But it turns out with the hub half white and half black, you get one pulse, you get one transition per rotation. What I'm going to show you in a little while, or what we're going to talk about, is that with a sample data system like this, the longer between measurements, the less stable the system is, because you have to wait for the next measurement. Therefore, coloring the hub with white on one side and black on the other side is just about the worst possible way to make the measurement. It's what I tried first because it was easy. It would be better to do this. Then you get two transitions. Another possibility, you look at this, how many blades are there? 1, 2, 3, 4, 5, 7. 7? 7 blades. 7 blades, except for the 2 or 3 that have had a blade knocked off by a screwdriver. 7 blades. Well, why not paint a white dot on each blade? And then divide by 7, of course, you get the RPM. But one group last year had a much better idea, and you can use any of these methods. Instead of using reflectance, so in the way I set it up, this is supposed to be the fan, that's the hub, that's the axle, this is a side view. I had the the photo emitter here and the LED here. And by the way, if you set it up this way, the angle of emission of this emitter is only about 10 degrees. The angle of acceptance of the sensor is only about 10 degrees. So you better get them pretty well lined up, or they're not going to see each other. Now, white paint is nice because it's dispersive, and so you don't have to be very accurate because it makes a big flash of light. These are pretty bright LEDs. It's up to 100 milliwatts infrared. Suggest you might not want to put it right next to your eye and stare at it. So what they did instead, what this one group said is, well, that's a stupid way of doing it because it depends on reflection and it only gets a couple of transitions per revolution. So why don't I put the emitter on one side and the photosensitive transistor on the other side and just have the blades chop the light and look at transmission. And that worked very well. You can do it any way you want. Pretty much, yeah. Use the blades for what they're good for. They're painted black. They probably don't pass much light. Now, you want to be a little careful about the direction you point this transistor in. You probably don't want to point the transistor directly at the fluorescent light. There's not much infrared that comes out of those, but there is some. The other thing is that you can tell if the infrared emitter is working because most of you carry a camera now, and it turns out that silicon cameras are sensitive to infrared. Now, also, though, most cameras have a filter in them that explicitly gets rid of the infrared in the image for various reasons, among which is that infrared doesn't focus necessarily at the same plane as visible, so you get hazy images. But they normally pass enough light that you can, if you take your cell phone camera and get directly in line with the LED, you can see a little bit of kind of purplish light coming out of the LED, it looks like, and you can see if it's running or not. You can get a little bit. What I recommend is that you start by building the circuitry. Build the motor driver. You don't have to have any software running to test it. Once you know that the isolator is working, once you know that the microcontroller side is isolated from the motor driver, hook up the motor driver to VCC. Hook up the isolator, the opto isolator to VCC. See if the motor starts to turn. If it doesn't, you've got a mistake in the circuitry. Debug that before you even start with the software. Once you've got the motor running, then work on the sensor. You have the input to the op amp and the output of the op amp that you can put an oscilloscope probe on. Do it. Look at the waveforms. Get that working. When that's working, hook it to the motor. It should drive the motor. There's kind of a strange, weird feedback here, but if you just have the sensor looking at the emitter with no motor in the way, then you can turn it on and off by moving your hand in between it. At that point, you've completely debugged all the electronics. Now you can start on the software. Isolate the stuff you need to debug as much as you can. Debug in a modular fashion. Debug little pieces. Debug the motor driver. Debug the transistor, the output transistor, before you add the opto isolator. Add the opto isolator. Debug that. Put it together. Test it every step of the way. Save yourself some pain. Any questions about Lab 4 at this point? I was interested to see that there were precisely 3 people in lab this morning. There are office hours from 10 to noon today, as always on Wednesday. That implies to me that the level of fear is not very high right now. Now that's sort of understandable because all next week you're laid back. It's really not 3-week lab though, it's a 2-week lab. Because most of you are not going to be here over spring break, and we're not. Again, any questions? Well, let's talk more about motors. I sort of gave a kind of a hand-waving introduction to PID control last time, but we ought to do a little bit better than that. And so I want to spend a few minutes talking about control theory. So motors. Let's come up with a model for the motor first. We have some voltage source that we're going to hook up to this battery. And we're going to model the motor as some resistance. After all, every wire has resistance. Some inductance. And then a back EMF generator. So this part is the motor. And the reason that there's a back EMF is that, after all, every motor is also a generator. You spin the motor, you're going to get a voltage out of it. So we're going to base our model on this simplified version of a motor. Let's say that the back EMF is given by some constant we don't know yet, times the angular speed of the motor. Theta is the phase angle of the motor, so theta dot is the angular speed of the motor. And another fact that we just need to know about motors is that the same constant, more or less, times the current. This is now current. This is not the square root of -1. This is the current. Times some constant, which happens to be the same constant, gives you the torque on the motor. So that's torque. So there's 2 equations we need to consider here. One is equivalent to F equals ma. It's torque equals moment of inertia times angular acceleration. Remember that from someplace? So if we have some moment of inertia of the motor times the angular acceleration plus some drag coefficient times the angular velocity, that's got to be equal to the torque, which is equal to k times I. So that's force law, torque law. And then we can also write Kirchhoff's law for this circuit, which is that L di dt plus R times I has got to be equal to V minus E, which is equal to V minus K times theta dot. So torque equation, Kirchhoff's law. And we can eliminate the current between these and grind away on the differential equation for a while. So remind me, where do you learn about Laplace transforms?
21.
All right, so you know that stuff, at least in principle. So I'm going to write the Laplace transform of this thing, and we're going to write this as some. Actually, we're going to write it as a spectrum. What's the matter? Don't remember Laplace transform? Don't remember, or why? You probably never learned. You probably never figured out why you learned it in the first place. In fact, haven't used it since, right? But you will today. And that is that this is some now this is sort of like, this is the frequency domain. I don't know how to write this. Let's write these as vectors. These are phasors. Actually, we're gonna solve this as phasors. It's some k over j, big J, j omega plus b times L times j omega plus r plus k squared. J is now the square root of -1. And you can sort of look at that and say, well, it's a second order system, right? There's 2 powers of j there, of omega. And you can guess, who'd like to guess what the natural frequency is? It's whatever the coefficient of omega squared is, right? So it's something like j times L, right? So like the square root of j times L or something like that. And at that point, now we can get rid of the circuit because we've abstracted everything away into some sort of ungodly power spectrum. But let's now draw out the Bode plot for that. Yes? Question?
Isn't it divided by 2 the natural square root of JL divided by 2?
Yeah, so something like square root of JL. There might be a factor of 2 in there. Yeah. So of course we can log omega. Remember Bode plot? Log omega versus the log of the ratio of the magnitude of the ratio of theta dot over V. And if we plot this function out, we'll find that we get something that is, when omega is small, we get something like 1 over k. Right? Not quite. There's another factor in there, but it's a constant. So if we're much less than the square root of JL, we're going to have some constant level, and then the amplitude is going to start to fall, and at high frequencies the omega squared term is going to dominate there, so the slope of this on a log-log plot must be -2. Right? Slope of this equals -2 on a log-log plot because this is equivalent to 1 over omega squared. Right? Hooking together. The log of 1 over omega squared. Yes. Say again? Yeah, 20 dBs per decade is also if slope of -2 on a log-log plot if both axes are in decades, right? So, well, that says that if you apply a sine wave changing voltage, after all, this is all once we start going into some sort of frequency domain description, we're saying that we're working with single sine waves that are driving the motor. So as we go up in frequency, the ability of the motor to follow the drive voltage decreases until at high frequency it goes to a constant value. It can't follow changes at high frequency. But there's more. What's the phase angle? The phase angle of this function. So let's call this the natural frequency there. So what's the phase angle of this function at low frequency? 0. What's the phase angle at high frequency? Say again? 180. Or pi, as we sometimes say. Yeah, 180 degrees. So at high frequency, so at low frequency it's 0, and at high frequency it's minus 180. And so what would you guess it is at the natural frequency? 90. So it looks something like this. Well, it's a little crummy there, but it's smooth. So the motor response, as the motor drops in amplitude, ability to follow the input voltage, it also lags the input voltage. That's what phase angle means, is that it not only is it the amplitude going down of the response, but it actually is changing later than the input sine wave. Question?
No, we're calculating the natural frequency.
Okay.
It's K.
Did you differentiate and set equals 0? Or how'd you?
That is the second order equation, right? So it's s squared plus 2 zeta omega n plus omega n squared.
Okay.
Where omega n is equal to omega n squared is equal to k squared. So omega n is equal to k.
Cool. Now, there's another phase. So that says that there's a phase shift at high frequencies. And why does that matter? Well, it matters because we want to control the speed of the motor, and we're going to have an input here which is the desired speed. And we're going to have some feedback which is the actual speed. So you're going to be measuring this. You type this into the keyboard. This you choose. This is the actual feedback. There's going to be some motor out here. The output of the motor then is theta, which is being theta dot, which is being fed back. And then we have to have some controller here, yet to be determined. Great. I love it when my cell phone goes off in class. Well, it'll stop after a while. Or not. Stop it. Yeah, well, one time I had just chewed out a student for having their cell phone ring in class, and mine goes off. So I don't chew out students anymore for that. So as I think I was saying, before I was so rudely interrupted by my cell phone, we want to build a command program that's going to take the desired speed, subtract the actual speed to form an error term, apply this to some control function, which is then going to apply some voltage to the motor, which results in an RPM, which we can then compare to the input. The problem is that if we get a phase shift of 180 degrees at some frequency, this subtraction becomes an addition. Right? The sign of this changes, the sign of this addition changes, and the system becomes unstable. That's a bad thing. So that's why it matters. But let's work on this just a little bit more at this point. So so if we call this well, let's call this output here. And let's call this, what did I call this before? M of f. And let's call this control C of f. And then we can write that the output as a function of frequency must be equal to C of f times M of f times the error. Or that output of f is equal to C of f times M of f times the input minus the output. Just call it out. And we can solve this, and we find that, so the output here then is given by some input. This is the input times C of f times M of f over 1 plus C of f times M of f. So M of f has some value at a bunch of different frequencies. But if we make the product of these big enough, if CF times MF is big enough at any given frequency, then the ratio is approximately 1 here. In other words, the 1 becomes negligible if CF times MF is big enough. If this ratio becomes 1, then the input is equal to the output, independent of everything. Right? Doesn't matter what the motor's doing. Doesn't matter how much load you put on it. If we make this product big enough, then the output is equal to the input. That's what we want. We want to be able to command a voltage. We want to be able to command a speed. And we want that speed to appear at the output of the motor independent of everything else. Oh, well, that's easy. Just make C of f equal to something big gain. Big. A is equal to big gain. And that'll work. Except that the more accurate the bigger you gain, the more accurate the system will be. The more closely the input will be equal to the output. But also, the more likely you are to have, you're taking this curve, you're moving it up to higher values because you're multiplying it by some big gain. I won't draw too much on the wall because K doesn't like that. And at some point, you're going to get to the point where the gain of the system is still bigger than 1, and the phase shift is going to be equal to 180 degrees. And at that point, this loop will become an error amplifier, and the error will increase without bound. Oh dear. That's not good. So, what does this mean in practical terms? It means that if A is small, and you step the input, the output will look like this. If A is bigger, you step the input, A will look like that. It'll become more accurate. It'll be the static level of the response will be closer to the input because this product will be bigger. We make A a little bit bigger. And the system will start to overshoot a little bit and then decay back to a steady value. And you make it yet a little bigger, and you'll get self-sustaining oscillations that will grow without bound until you saturate the system. And in terms of our system, what that means is the motor will alternate between stopped and 3,000 RPM. Stopped and 3,000 RPM. All right. Clearly, you want to pick something in this region for A. If you possibly can. Turns out that by the time you get A big enough to get into this region where you have good response time but not too much overshoot, that the system is hard to make stable.
Root locus?
You know, I tried to solve root locus for this, and it's really hard to get it accurate because there's an extra phase shift which is velocity and is speed dependent. And that is the time it takes to go from one reading pulse to the next is a delay. And the delay is equivalent to a negative phase shift, which depends upon motor speed. So that low speeds have bigger phase shift. And my analysis wasn't up to that, although I think it's solvable. Yeah.
How did you, when you catch your root Lucas?
Rot Lucas?
It's been a long day.
I like it.
What did you use to characterize the motor? How did you get like?
Well, there's another problem here too, and that is that the motor is only piecewise linear. Because when it's under power, you have this RLC model, and when it's turned off, you have a passive exponential decay model. And I just couldn't figure out how to put it together. So that's why I wrote a MATLAB program to simulate it. Because I figured I could do that more easily than I could figure out how to do the piecewise linear stuff. But I'll bet one of you can do the piecewise linear stuff.
How do you find the filter coefficients in MATLAB? I'm curious.
What filter coefficients?
So you have like what looks like a firework filter?
Oh, I guessed the time constant of the motor.
Okay.
And the way I did it was, I spun it and I watched it spin down. Slightly more, I mean, it's slightly more quantitative than that. You put the photosensors behind it, you spin it up, and you watch the decay curve, right? And it's about exponential, and the time constant is something like a second. You can get the actual decay time for your motor by doing exactly that. Set up the sensors, give it a spin, and watch it spin down. So the way you can fix this, the way you can stabilize the system, is don't make C of F just a pure gain. Give it some phase shift. And we have too much negative phase shift here. That's why the system is oscillating. So what we need is a little bit of positive phase shift. Well, what could you do? You could, remember the motor looks like this. It's cutting off at high frequencies. So what if you were to add a little bit of gain at high frequencies? What if your controller, C of F, looks like this? So at about the frequency where the motor starts to drop off in amplitude, you add a little bit of gain at high frequencies. So at high frequencies, it looks like the slope is 1. And at low frequencies, the slope is 0. So what kind of circuit has a slope of 1? Plus 1? Oy. Well, let's see. D sine omega t dt is equal to omega sine omega t plus 90 degrees, right? Yeah? So, at high frequencies, at every frequency, this has a slope of plus 1. It is proportional to omega. Remember, this is log omega here. So this is proportional to omega, to the first power. And it has a phase shift of 90 degrees, positive 90 degrees. Wow. If we were to multiply these two together, then the phase shift down here would be about 0. The phase shift up here would be about minus 90, because plus 90 times minus 1. Minus 180 is the phase shift here, plus 90 is the phase shift here. We would have a system that never passes through 180 phase shift, and so it never becomes unstable. So if we set then the CF function equal to A, well, let's actually write it in the time domain rather than times the error plus some b times an approximation of the first derivative, error dt, delta t. We will build a function which is a constant at low frequencies. That's this part. Has a constant gain at low frequencies. And at some cutover frequency, which is determined by some ratio between B and A, it will become a differentiator. And it'll become more stable. Yes? That's T. Now, you can mess with A and B, you could tune this back and forth, but a good guess is that you're going to want to tune this breakpoint. You're going to want to tune the breakpoint here from where it becomes a constant to where it becomes a differentiator to something like the natural frequency of the motor. So you're going to want to tune it to something like 1 radian per second. Now empirically, how did I mean, when I set this thing up, how did I tune it? Well, since it was so weirdly not, piecewise linear and had this odd delay term in it, I started jacking up A until it started to oscillate. And then I turned down A a little bit. And then I started turning up B and see how much more I could turn up A. And did it completely empirically until I got a stable system that settled quickly. However, a couple of students last year managed to come up with an analytical model and tune it analytically. So you can stabilize it. You can stabilize it. And, oh yes, in terms of efficiency, there's no particular reason to divide by delta t every time. You can merge delta t and b together. Save yourself a division. The control loop here doesn't make any sense to run faster than the sample rate. And the fastest RPM you're going to get on this motor is around 50 revolutions per second. So it doesn't make any sense for your control loop to run faster than about 50 hertz. That means you have time to do floating point arithmetic, should you desire. Don't have to. You can use all scaled integers, but you do have time to do floating point. So the actual computational form here, as I wrote before, is going to be that you have a times some error plus some scale b times error at t, error of t, minus error of t minus 1, plus some integral term, some integral term. And the way this is generally written is that for stability is you take the min of some I max. In other words, you do not allow the integral to grow without bound. And compare that to some I times the sum from t equals 0 crossing to n, error n and you set this to 0. The most efficient way to set this to 0 is when the sign of the error, the SIGN of the error, is not equal to the SIGN of the integral. So when the error changes sign relative to the integral, you treat that as a 0 crossing and 0 the integral. And C of t equals 0 if the error is less than 0. Integral. I just got tired of writing. Or let's just make this the sum. That's this sum here. So the effect of this term is hopefully to get rid of small static errors. After a step, if you have a fairly large static error, this term should slowly decrease the error to a constant, to 0, or at least in principle to 0. Now, due to the piecewise linearity of the system, I don't think you can make this hover stably near at any reasonable percentage of the commanded voltage, but you can have it hunt up and down near the commanded amplitude, the commanded RPM, and I think you should be able to get that within a few RPM, certainly within a few dozen RPM at 1,000. And again, we're going to be testing it around 500 and 1,000 RPM. That gives you some way of, you don't have to make the system stable down to 50 RPM, and you don't have to try and make it, jam it all the way up to 3,000 RPM, which is hard. So Monday, next logical Monday, I will talk more about tiny real time, unless there's questions about the control stuff. Yes? Yeah, the motor and diode circuit, yes? There is a large positive current, but it's not a huge current because of series resistance. I mean, it doesn't try to go to infinity. What do you want to hear about next time? How many people how many people think they're going to be here on Friday? Oh, still, a dozen. I saw that over there. That was one of these things. It depends. I see where the priorities are here. So, anything you want to hear about? Okay. So we still have 5 minutes here. So let me talk a little bit more about final project. If nobody has anything to say here, and that is, we're going to get your proposals you do this week. We're going to give you back the proposals in lab next logical week, and then the first parts order will be the following Monday. All right, so I'll put in an order to DigiKey up to $20 per group of what you want. It doesn't have to be. I'm going to be ordering weekly. You get one shot, $20 for the whole project that I'll spend for you. The nice thing about that is you don't have to pay shipping. You buy it yourself, that's fine. You have to pay shipping. So think about what you actually need. We will expect progress every week, yes? As I've said a bunch of times, and is outlined in Lab 5, which you better have memorized before the end of before next week. There's a pile of rules about what you can do and can't do. And the reason there's a pile of rules is that over the years, students have figured out ways of gaming the system. Oh, you didn't say that we couldn't use this, and so that's why the interconnect leads, those nice little leads that have headers on each end, are $1 each in the budget. It's because I don't want somebody, because in past years when I didn't charge for them, people use 100 of them. They're $1 each in the final design. This encourages you to solder. Soldering is more reliable, and you can take it home with you. It's why power supplies have a budget value, because people were using 5 power supplies. We were running out of power supplies. Oh, I need them all. So I try and figure out ways of keeping students from gaming the system, while the students try and figure out ways to game the system. And don't try and do that, though. What if I spend $75.02 How many points is that going to take off? Go look it up. You'll be shocked at how little it is. On the other hand, because it's actually a quadratic function of the price over $75, and it's normalized to be 10 points at $85. $10 over will cost you 10 points, one whole grade. 10 cents over will cost you 0.01 point. Or less, yes?
When you're saying all these like points and also like for example finishing early, for example bonus points,
Uh-huh.
are all these points like out of 100 for the final project or it's out of 50 points?
You're going to be graded 0 to 100 on the final project, and these are all out of 100.
Okay.
And then that'll be normalized down to 50% of the final grade. The way we do the grading is we first assign the quality grade, how good was the project, how good was the write-up, then we add bonus points. But nobody goes over 100. Now curiously, the projects that are sort of best thought out and that work the best are often get a bonus for being early because people were well organized. But they don't go over 100. No grades are over 100. The procedure for grading is that we will the TAs rank order the projects in their group, and then we get together as a group of staff and we rank order all of the projects, and then we assign a value to the top projects and to the bottom projects, and then we fill in the middle. It's about 4 hours to do that. That's after all the projects have been read and evaluated, right? So we can make approximations about what a project is worth, but it's hard to get a, is this going to be a 93 or a 95? I don't know. Depends on the competition. Work steadily. You don't have to kill yourselves for this. I don't expect you to kill yourselves for this. But I do expect you to work steadily. 12 hours a week. There's going to be nothing else you're expected to do for most of the month. You don't even have to come to class. You do have to be in lab 12 hours a week. See some of you Friday.